I want to make some comments about the water balance equation for a watershed, especially with regard to units and how we deal with the different um, descriptions of fluxes in and out. So this is supposed to be a three-dimensional picture of a watershed. There's a couple trees there. Those are my attempts at trees to show you that we're looking at a supposedly a three-dimensional picture. And remember that in the water balance equation, we'll have the inputs will be consist of we'll have precipitation in, and we'll always have evapotranspiration out, and then this main stream will lead to stream flow out. We usually give it the symbol QS. And then we could have underneath the ground here groundwater flow in or out. And those are the major inputs and outputs to the watershed. So the water balance equation is that the change in storage over some period of time has to equal the inputs minus the outputs. And typically we use symbols that look like this. P for the input, and then outputs. Well, I'll describe groundwater flow as an input. So we'll put groundwater flow in as well, minus evapotranspiration and minus stream flow. Now, this is actually the way the equation is very commonly written, and in many ways, it's actually not ideal because it sort of doesn't actually do a good job of explaining that to use this equation, we need to have all the same units for every term. And the problem is that the way we describe the units of precipitation and groundwater flow and evapotranspiration and stream flow are very often different, but they need to be exactly the same in order to add and subtract them together to get the change in storage. So let's just be really clear that in this equation, change in storage is a volume, change in time. So all of these terms should have dimensions of volume per time. They should all have dimensions of volume per time. Every one of these terms has to have a dimension of volume per time. In the metric system, that is commonly, but there are many choices, right? But we might use meters cubed per year. That's actually pretty common because we often are looking at this equation over a long period of time, but we don't have to be. It could be a month, it could be a day, but typically it's sort of a year. In the English system, we might use cubic feet per year. Again, it doesn't matter exactly what the specific unit is, but it's got to have dimensions of volume per time, each one of these terms. Now, let's think about how we would go about measuring these because they're measured very differently. And I'm going to sort of exclude groundwater flow here just for the second because it's almost impossible to actually measure groundwater flow. It's almost always inferred by this water balance equation. But let's start with stream flow. So this is actually pretty easy. The stream is rushing past us right here at this location, and we have methods that we will describe later in the course for actually measuring the volume per time passing by this point. We're measuring all of the stream flows going right by that point there, and we measure it as volume per time. This is how we measure it. In the metric system, that's often cubic meters per second. In the English system, we often use cubic feet per second. I'll just write it like this, cubic feet per second or cubic feet per minute, and that's often abbreviated as CFS. That's what that stands for, cubic feet per second. So it's a volume per time. However, precipitation and evapotranspiration are not fluxes that are occurring at a specific spot where it's easy to go and measure, right? It actually varies all over the watershed. Let's think about precipitation. It could be raining. It could be raining differently over here than it is over there, right? It's something that applies over the entire watershed. Now let's think about the problems of how we actually want to get it. Remember, we want a volume per time. So let me create a sort of a scenario here. Let's say I call up my colleagues in the School of Geosciences, and let's say I have three colleagues. Let's say Connie lives out there. This is where Connie lives. And Kamal, he lives way over here. And Sarah lives over here. Well, those are my colleagues. These are actually people, okay? And I call up Connie and go, "Wow, Connie, it rained a ton yesterday. How much rain did you get?" And Connie says, "Well, I had a paint can sitting out on my, a paint can sitting out on my porch, and it was empty. And then after it rained, I got, oh, I don't know, I got zero point 0.5 cubic meters. She's a scientist, right? Cubic meters of rain yesterday. Wow, that's a lot, right? And then I call up Kamal, and Kamal says, well, I happen to I had a 55-gallon drum sitting out in my backyard, right? Big 55-gallon drum sitting in my backyard. And when that thing was, after the storm, I got 6 cubic meters of water in my drum. Wow, that's a lot more than you got, that Connie. And then I asked my friend Sarah and says, well, I put a coffee cup out on my porch when it started to rain. There's my little coffee cup. And I don't know about you guys, but that's supposed to be a little tiny coffee cup. But at the end of the storm, heck, I only got 0.03 cubic meters of water in there. So we all got really, really different values, right, for measuring the amount of rain that fell. Remember, what we want is this term here should represent the total amount of rainfall that falls on this entire watershed. And I'm sampling it a little bit over here, and I'm sampling it a little bit over here, and I'm sampling it a little bit over there. But somehow we're going to have to figure out how to get an average over the whole watershed. But the reality is that I can only measure it at given locations. I can't measure it everywhere, right? And how I measure it's going to give me really different answers. I mean, how useful is the information to say, hey, I got 0.5 cubic meters, that's the volume over here, and I got 0.6 cubic meters over here, and 0.03. It's not useful at all. However, what if I'd asked the question instead? Well, that's crazy. I can't compare those things. Well, let me ask you this, Connie. If you're assuming your paint can was empty, how much did the water level rise in your can, right? So here's my paint can. Here's Connie's paint can, right? And I ask instead, okay, at the end of the rainfall event, your can had some water in it, right? And you said it was 0.5 cubic meters of water. But forget that. Just tell me, how much did it rise? What was what we call the depth of rainfall? And Connie says, oh, I got 1 inch of additional height. The water level rose 1 inch in my paint can. And then I go to Kamal, and Kamal goes, well, what about you, Kamal? And Kamal goes, oh, I got 1 inch too. But of course it was a much bigger container, so 1 inch was a lot more water. And then I go to Sarah, and Sarah go, hey, in my coffee cup, I got 1 inch too. So actually, we're actually measuring then in these 3 places. Oh, one more thing, I could then say, okay, everybody seems to have gotten, whatever container they were using rose 1 inch. What if I actually now call my friend Chuck? Here's Chuck over here. Chuck, he doesn't have a can or a paint can or a teacup, but he's got a great big swimming pool. And I go, Chuck, go out to the backyard and look at your swimming pool. How much did the water level rise in your swimming pool? And Chuck goes, it went up 1 inch. And so now I have a pretty good idea that over this entire watershed, water fell from the sky, the rain, that lifted the level of water 1 inch, no matter how big the container was. That's how I measure precipitation. So precipitation is measured as this depth of precipitation. And to convert that to a volume, let's just think about how we would do that for any of these containers. Let's take Connie's paint can here, right? That's a terrible picture. Let me try to redraw Connie's paint can here a little bit better, okay? So here's the paint can. Okay, hold on a second. Okay, there's a little bit. So there's her paint can, and it's got some water in it. So the volume of water, the volume of water here will equal, for all of these shapes, as long as the walls are vertical, will equal the area of the base A times the depth of precipitation D. So what actually sort of measured here in every case is 1 inch, was the volume of precipitation divided by the area, or the volume per area. This is actually how I measure precipitation. I measure it on a volume per area basis, and the dimensions of volume per area. Volume has dimensions of length cubed, right? Like meters cubed or inches cubed. And area has dimensions of length squared, like square meters or square feet. And so when I take volume divided by area, I get length. So I get the length over the time that it took. In this case, in the example I gave, 1 inch per day, right? So I got 1 inch of rain per day. So that represents the volume per area. If I want to convert that into actual volume, let's just write this all. I kind of made a mess of this. So let me write it again over here. So over here, I have that the depth of precipitation was equal to the volume of precipitation, V, divided by the area. And if I want to find the volume, I take that depth, D, which was 1 inch in this case, and I multiply it by the area. So since I'm multiplying it by a bigger area, so for example, Chuck's swimming pool, that's a lot of water filled his pool, right? It was 1 inch of water, but his pool was huge and had a big area. So the volume of water, that extra water that was in his swimming pool, was equal to that 1 inch, right? This is 1 inch of rain, it fell for everybody, times this very large area of his swimming pool. That would give the volume of water that entered Chuck's swimming pool. In contrast, for Sarah's coffee cup, it would be a really small volume, right? Because I'd take that same 1 inch and I'd multiply it by the area of her, the base of her coffee cup, which is really small. So this relationship here is what we need to use for precipitation. Now, one more thing I want to point out here. Let's take Chuck's swimming pool, right? So Chuck, in Florida, for example, we typically get 50 inches of rain, precipitation, per year. So do you think Chuck's swimming pool level rises 50 inches per year, which is almost 1 inch per week? The answer is no. If you go look at Chuck's swimming pool, that on average, Chuck's swimming pool stays about the same level. And the reason is because as much water is entering Chuck's swimming pool as precipitation as is leaving by evapotranspiration. And evapotranspiration has the same kind of idea as precipitation in that it's something that varies all over the watershed, but we can only measure it at a given location. So evapotranspiration, in the same way as precipitation, is described in terms of a depth, a length per time. So if Chuck's swimming pool received 50 inches of rain a year and its level didn't change, then it must have experienced 50 inches of evaporation per year. I should probably just say evaporation because there's no plants in its pool, right? So it's just pure evaporation in that case. So the evaporation rate was 50 inches per year. And the same way that I can do this with precipitation, if I want to get the volume of water evapotranspirated away, I would multiply the rate in depth per time times the area. So I would use the same ideas for evapotranspiration as I use for precipitation. So let me sort of finish this up by pointing out the problem again with this equation. I'll highlight it in red, and then I will write it again on the next page and go over what the problem is. Okay, here's our equation again. And once again, let me remind you that everything here has to be in units of volume per time, every one of these terms. And we've already said that stream flow here is almost always measured in terms of volume per time because that's how we measure it. This is measured. So we don't have to do anything. We may have to convert units. That's another story. But at least it's measured in terms of volume per time. But precipitation and evapotranspiration, even though we just use the symbols P and ET, are very commonly or are almost always measured as rates, right, of length per time. And we need to multiply by the area of the watershed, like I just described in the previous 10 minutes, right? Groundwater flow, again, is usually not measured at all. It's almost always inferred, and we describe it as a volume per time. But the problem is that in this equation, it's not immediate. If we just use the symbols like we normally do, it's not immediately obvious that we can't just add P and ET and QS together because they're actually measured in different units. I'm sorry, measured dimensions, I should say. P and ET are length per time. Q is in volume per time, and that's really not very ideal. So to correct that or to make it obvious, in some cases people will use a different symbol, a special symbol to always mean volume per time. And there are a couple choices here. One is sometimes people use the Greek symbol mu, and this just means volume per time. The other thing we can do, and sometimes I actually prefer this, is to use the symbol Q, which also means volume per time. And we've already used that. That's what this Q sub S means. It's the volume per time of the stream S. So using that symbol, one of those symbols, we could rewrite our equation. This is just using different symbols, but hopefully that makes it clear as, let's use the mu symbols here. Mu. So here I've got the mu symbol convention on the top and the Q symbol convention on the bottom. And these are exactly the same equation. This is exactly the same equation that I've been using before. It's just I've tried to use symbols that make it explicit that all of these things have to be in the same dimensions. All of these things have to be volume per time. And so if we keep that in mind when we use the water balance equation, we won't run into the all too common problem of students trying to say, okay, I've got Q of 35 cubic meters per year, and I want to add that to precipitation, which is 1.5 meters per year. And they try to add those two things, but obviously you can't do that because one is in cubic meters per year and one is in meters per year. And the problem is our symbols here. We use P to be precipitation, typically measured in length per time. We use Q to be stream flow, typically measured in volume per time. But in order to use the equation, we need consistent dimensions of volume per time. So we have to make the point. We have to understand that we have to wrong word. We have to calculate the volume per time caused by precipitation and evapotranspiration acting on the entire area of the watershed by multiplying those values in length per time times the area of the watershed. All right, that's probably a longer video than I intended to make, but hopefully this helps explain the sort of subtleties of dimensions and units when using the water balance equation.